Can we all see that? I'm going to assume that's a yes because I can no longer see folks. So I'm Christopher Liljenstolpe. I'm the, as I said, CTO and solutions CTO for solutions and co-founder at Tigera, which is the home for Project Calico. You can my Twitter handle and GitHub handle, etc. And before we get going, of course, we have to wish a happy 156th birthday to Fridtjof Nansen. And if you know enough about me, you'll know why I specifically call off Fridtjof Nansen. But I've done work in the polls before. So happy birthday to Mr. Nansen. So solutions utopia. You know, I think the issue I'm going to talk a little bit about is what's the advantage of policy? Why might you want to deploy policy or application connectivity controls within a Kubernetes or cloud native environment? You know, you've developed your applications, you've deployed them as containers into Kubernetes pods, and those pods are up and running and everything works. So that's, you know, it's a great environment for doing that. But there are, once you start getting into production in a large enterprise or as part of a larger organization, there are other components in your organization that also need to be involved in this. That might be the security team, the ops team, risk assessment. There are other groups that need to have, to do their jobs, need to have visibility and the ability to interact with your new cloud native application environment. And the way that was done often before was very waterfall in its approach. If you take a look at earlier models, you deploy an application and then you'd ask the firewall team to approve firewall changes, or you'd ask the ops team to take over that application, program the network, program the physical infrastructure, etc. That really doesn't fit in a cloud native model where applications can mutate very quickly. It's a constant delivery CI/CD kind of environment. The orchestrator itself, like Kubernetes, is auto-scaling and auto-repairing infrastructure. Classical anchors, things like IP addresses, etc., now become fungible. All of those things, and you know, even larger than that, is the dynamicism of these environments. If the orchestrator is firing off auto-scaling groups, etc., and repair and red-blue testing, etc., that can be happening in almost real time. If you have to be updating infrastructure policies, etc., those can take hours, days, or longer if you've ever raised a firewall ticket in your organization. I'm sure everyone's organization has, you know, that's not a problem at all, but I can assure you in lots of other organizations, it might take you a bit of time to get a firewall change approved. I'm sure that's not the case here, but you know, that's what happens very often in the real world. So those time scales are very different. So you sort of lose the advantage of a cloud native environment. So how do all these groups now still do their job? It's a necessary job in this cloud native environment. So let's go back actually a little bit and take a little bit of a retrospective in the past. I'm going to use a really nasty word, and it's SOA. It's been around for a long time. We always talk about how cloud native is new and service meshing is new. It actually isn't. You know, so service-oriented architectures have been around for a long time, and the idea is you split up processes into individual components, and you make those components able to communicate with each other over some kind of infrastructure. And you know, that infrastructure has moved obviously over the years from being RPC calls within a piece of code into being over the network. So that way these processes can be individually scaled, distributed, etc. This is, you know, this is the nirvana that we've been working for quite some time. give you an idea of how long, and my guess is not all of you on this call have been in this industry this long. I guess I'm going to date myself by saying I have been. So we've seen this story before. And, we started off with this thing called Corba. And again, the idea was you'd have objects, but those objects had to basically be completely refactored in order to collaborate in a Corba environment. You had to write your applications from ground up around Corba. And so surprisingly enough, that really didn't take off because it's sort of hard to tell people to completely refactor their applications in order to make something work. And everything within the infrastructure has to support Corba in order for Corba to be to have been successful. So of course, that's never going to take off. So we tried again with something called enterprise service buses, ESBs. This came around sort of the Java world. Slightly more successful, but really not much, because again, I have to write my applications to use the ESB constructs. And it's very difficult to bring other objects, other code, legacy code into that kind of environment. Everything has to be written with ESB in mind in order for ESB to be successful. So again, this one sort of failed. So what's different? And what's different, we started looking at in 2010, API management, API gateways. And what we basically started saying is, instead of building a whole infrastructure, let's just manage access to the APIs. And this got somewhat better, but it still required writing your applications now to integrate with that API gateway, etc. But at least now you could use different APIs and register different APIs. But it still was, it requires some amount of refactoring. Between that time and now, things have changed a little bit. So what's changed is one of the advantages of having middle boxes in the internet, load balancers, HTTP load balancers, firewalls, etc., is that those applications that are meant to be used on the public internet have had to deal with things like load balancers and firewalls. They're a necessary part of the infrastructure. So we've started writing applications to utilize the APIs that work across those devices, namely HTTP and its successors, HTTP1, HTTP2, gRPC, etc. So we've now basically already refactored our applications to deal with the modern internet with a common API framework, HTTP, gRPC, etc. So that, along with internet scale things and what we've done with Kubernetes, etc., you start looking at the way microservices look today. We already have the building blocks to build this kind of environment. Applications are limited in scope. We don't write big monolithic applications anymore. We write containers that are limited in scope. You don't, or even if it's not containerized, you basically break up your applications into small constituent components. You publish those APIs, and something we do quite regularly already. Things are independently deployable, and there are components that can exist outside of the process itself. So for example, we're already used to using things like load balancers that aren't part of the code. We don't put load balancing code in our applications anymore. We rely on external components. Those might have at one time been an external actual load balancer, like an F5 or an A10 or Nginx or something like that. But we already are doing many of the things that we need to deliver this service architecture already today. We want things to be independently scalable. We've been doing that trying to do that for quite some time. I want my web front end servers to scale independently with my back end databases. So we've already gotten to a lot of this infrastructure components that we need to deliver on the original goals of thinking about things in terms of services and an architecture based on services rather than an architecture based on deploying servers and monolithic applications. We now want to think, we now have these components that allow us to finally start thinking about things as services. So what is SOA today? And I'm using SOA specifically because I'm just trying to point out that we basically delivered finally on what people have been trying to do for the last 20 plus years. And we are using microservices across the network, using common APIs and using capabilities in the underlying infrastructure to handle a lot of the undifferentiated heavy lifting, as people call it. HTTP load balancer is an HTTP load balancer. It doesn't need to be specific, have specific knowledge to your application necessarily. So how do we deploy these applications today? Today, you can deploy these applications on physical boxes. You can deploy an application build up a bunch of microservices, containers, whatever, on a physical server. You can do the same deployment across virtual machines. And you can split those microservices up into individual containers and deploy them in a container environment like Kubernetes. So that sort of sets a little bit of a context, the way you might want to start thinking about what you're really offering with your code. And you're really offering services, and you really need an architecture that's going to support services. So this is a talk about networking. So let's talk about what components you need in order to have this kind of service-based architecture within from a networking lens. So this is the classical OSI network layer. And really what I'm saying here is at the very low levels, this is really an operational based environment. And as you get up higher up the stack, it becomes more developer oriented, less operational environment, operationally oriented, but all of these things need to be taken care of. So what we're going to talk a little bit about today is some of the tools you can use to deliver the network portion of this services or this application. I'll now start using the term application connectivity or services connectivity in a modern environment. So first thing we need to do is get packets, get those API calls, get those REST calls or gRPC messages between services and pods, delivering those services and between pods, etc. So we need some kind of connectivity layer. And that's layer 3 and layer 4 in the infrastructure. And there's a really nice tool out there, at least we think it's a very nice tool, called Project Calico that does that. And we'll talk a little bit about some of the capabilities there. And then we also need to start talking about things at a higher level. So now not only do I need to get the packets from A to B, I need to figure out where those packets need to go based on the application that they're servicing or the service they're servicing. So that you start looking at things like load balancing and endpoint or service discovery and possibly policy control at layer 5 through 7. Are you allowed to make that kind of API call? So that's what people are now calling service mesh. And there's a really nice tool out there called Istio that fits very well in that space. So we'll talk a little bit now about Calico and Istio and how they fit together and what their individual uses are for. So, the agenda, we're going to talk about service meshes and their components. We're going to do a demo and layer 3 and the demo's on Calico. I put the circle in the wrong place. And then we're going to think about layer 3 and layer 4 endpoints and reachability and policy control of those connections. So not only how do we get traffic between different pods and in from the outside and out to the outside, but should that traffic be allowed at layer 3 and layer 4? So that's what we're going to be talking about here. A couple of examples of folks who have all deployed some or both of these components. Google just announced that Project Calico is the underlying network policy infrastructure for GKE. Box, and obviously they're very big supporters of Istio as well. Box is using Calico, and we talked about using Calico in both container kind of environments as well as bare metal environments. We'll talk about that a bit, and why we can talk about bare metal a little bit, but Box is another large proponent of this architecture. And IBM Bluemix. Again, IBM's Bluemix container service is using Calico as the underlying network and policy environment. And they're also big proponents of Istio and contributors to Istio, and Istio is part of that platform as well. So let's talk about layer 3, layer 4 first, Project Calico. The idea behind Project Calico is networking should be simple and just get out of the way. You shouldn't need to be thinking about networking. It's, apologies to some of the other people in this space, but very often the networking world overthinks networking. And we like to put lots of knobs and controls and give you lots of different options, give you lots of different types of packets that you can transport. So we build overlays and meshes of overlays, and I think of it as turtles all the way down. You end up with overlays on overlays. So if, let's say, you use an overlay-based infrastructure for your Kubernetes networking environment on top of a VM environment that's also using overlays, pretty soon you've got 2 or more layers of tunnels in each other, sort of turtles all the way down, or sometimes we say it in networking, 1,400 bytes of header and 100 bytes of payload. So we tend to make networking overly complex. And there's historical reasons for that, but in today's world, it's all IP. It should all be pretty simple. So with Project Calico, we sort of went back to first principles and said the network L3, L4 needs to do 2 things. It needs to get packets from A to B, and needs to apply policies to control if the packet should be able to get to A and B. So we've split networking in Calico up into 2 separate problems, and we solve them differently. One is reachability, one is policy enforcement. So reachability, let's make that as simple as possible. It's called IP routing. We know it works at scale. There's this little network called the internet that proves standard IP routing works really well at scale. It's also really simple. So we build an L3 simple routed fabric that uses standard Linux tools. And if you understand IP networking in Linux, you can troubleshoot a Calico network. It's pretty basic infrastructure. We can talk about it in more detail, but basically we turn every node into a router and we just route traffic from A to B. So it's very simple. Because it's simple and it uses standard tools that have been built to handle the scale of the public internet, i.e. IP routing, maybe routing protocols if you need them, etc. You can scale to multi-thousand node production clusters from a couple of nodes in your basement. That's your playground. Same technology, nothing changes. It's all exactly the same thing. So it scales very nicely because it is simple. Then, independent of that, we layer in a security layer called, and we use policy enforcement. And the idea being, very often people in the networking world try and do some isolation with firewalls or virtual networks. And those are great for what we'll call coarse-grained isolation. Actually, they're not great, but they work. You can say this is dev, this is prod, this is test network. But what do you do if things need, let's say instead you do, this is project A and this is project B, but now you need something in project A to talk to something in project B. Well, they're on separate networks. So now you have to stick those 2 together. And then you need to stick a firewall in between them to say, only these things in A can talk to these things in B. And that's a little hard if the IP addresses, the number of A's and B's and the IP addresses of A's and B's are constantly changing. That becomes sort of difficult. So, I now have a firewall construct to handle finer grained policy that's not really cloud native. And I have these big chunky groups of A's and B's and C's. In a large-scale system, you should find one way of solving a problem, and you should use that for all instances of that problem. You shouldn't make people at 3 o'clock in the morning figure out, was it the coarse-grained isolation that failed or the fine-grained isolation that failed. So in Calico, what we do is we implement a policy that basically says things labeled X can or cannot talk to things labeled Y. And things labeled X could be dev, prod, test, or things could be labeled LDAP clients and Y could be LDAP servers. Or it could be application A authentication clients to application A authentication server. They can be as fine-grained or as coarse-grained as you want. The mechanism is exactly the same. So we have this very rich policy-based microsegmentation, which surprisingly looks a lot like a superset of Kubernetes network policy, because it is a superset of Kubernetes network policy. So that's one takeaway about Project Calico. Instead of trying to solve connectivity or reachability and security at the same time, we treat them as separate problems. We use the right technology to solve both of those at scale and at real time from a cloud native perspective. And that allows us to use the right tools for the right job. So endpoints, let's talk about what an endpoint is. An endpoint is a virtual network interface associated with a host or a virtualized workload. So the idea here is an endpoint is a connection for a IP, for a network. So in this case, for example, I have two applications. One's listening on port 80, one is listening on port 81. It connects to an Ethernet in the Linux hardware, which connects to a NIC in the physical hardware, and that goes out on the network. So you can have, in this case, two endpoints on one server. You can have, now if I'm looking at virtualization, I could have potentially 3 logical servers in one physical server, and some of those have one endpoint, some have 2 endpoints, and all of those endpoints are exposed over a couple of physical NICs. So what we do in Calico in order to make this work is we actually turn the Linux server into a router, and each container has its own interface. In this case, a Kali interface, which is a virtual Ethernet. And so each container is its own unique endpoint in the infrastructure. And it hosts its own applications. Because each container is its own endpoint, each application can listen to the same ports because they're going to have separate IP addresses. They're not all going to share the same physical server's IP address. So now as an application developer, if you've got multiple containers that both need to listen to port 80 in a non-Calico kind of environment, it's very likely that if 2 containers, each trying to listen to port 80, show up on the same server, you've got a problem. One of them is having to listen to a different address. In this case, that's no longer the case. We treat each container as its own IP server on the network. So you don't need to be aware of port conflicts or anything else. And this is the Kubernetes native way of doing things. It's the way Kubernetes looked at things. So how does this work? You have 2 hosts. They're connected to a network. They're running Kubernetes. They have multiple containers each. etcd is aware of those containers and those hosts. And it's aware of those because it's listening to the orchestrator. The etcd is being listened to by Felix, which is the Calico agent on each server. And Felix takes information in etcd, saying container C and container D have these addresses assigned to them. They're on host 2. Container A and container B have these addresses assigned to them. They're on host 1. And Felix programs the Linux kernel in order to turn the host into a router for container A and B and container C and D. And then if necessary, if we're in private cloud or in some public clouds, we might run a BGP daemon, which tells the rest of the world that container A and B is on host 1 and container C and D is in host 2. What this actually looks like is the routing daemon talks to the forwarding information base. The Linux kernel is the reachability. You know, who can talk to who, or not who can talk to who, you know, where are things in the network. That's also programmed by Felix based on information from the orchestrator. Felix also programs the ACL tables, which is where we do the policy enforcement, where we say, can A talk to D or can A talk to B? One thing that's important to notice here is policy is always done exactly the same way. If we go back in here, for example, the same rule that would allow container A to talk to container D would be used to decide if container A could talk to container B. There's no difference if the containers are on the same hosts or on different hosts or even in different data centers. The policy enforcement is exactly the same. And then to interact with etcd and add policies and other things, you would use kubectl or calicoctl, depending on what you're trying to do. And that will allow you to mutate or change the data store that drives Felix. So let's talk about policy a little bit. Policies, we'll go past profile here. Let's just go right into policies. I'm running a little bit short on time. What you have is in policies is you have a policy that basically says policy name, etc., and then it has a selector. And then the selector says if something is assigned a key value pair, a label in Kubernetes says role is database, then this policy is applied to it. And the policy might be it's an ingress filter, so it's filtering traffic coming in. It's going to allow traffic from things labeled role front end to port 6379. So that's basically going to say any workload, any endpoint in this cloud that is labeled role front end will be able to talk to any endpoint in this infrastructure is labeled role database. So role database is the selector, who this policy is applied to, and this is the action of the policy. Is what I just was talking about, and we allow the traffic. So that is policy in a nutshell, and network connectivity. Let's take a little look at Kubernetes components. So we've got a number of things on the master and in the workers, and you have pods, etc. Now we start adding things like storage and certificates and routing and security to these workers. And we also start adding things like admission control, authentication, etc. And in Kubernetes. And we'll talk about some of these in a minute. So Kubernetes networking concepts, you have CNI networking plugins. Those are things that listen to Kubernetes, listen to the kubelet, and program the network locally on the host. And that's something that Calico listens to get its data. We have network policy, which we just talked about. You have a concept of services. Services are now things you deploy in state in Kubernetes that this is a database service, and it might have one or more pods offering that service. So a service is a virtual construct that allows you to have a single anchor point or a single entity to represent one or more actual endpoints that offer that service. So this is when you start defining services in Kubernetes. You have ingress controllers. Ingress controllers allow traffic from the outside of the cluster to reach pods and more specifically, or more importantly, services. So you've now created a service front-end application that you want your users to reach. That's published as a service, and the ingress controller makes that available to the outside world. You also have kubedns, which is a way of discovering what services are available within the cluster. So let's talk about now some of the things we can start doing at this services layer, and that's Istio. What is Istio used for? It's used for traffic management. So somebody's asking to reach a specific service. Where do we send that traffic? How do we load balance it to the individual pods? Are the pods alive? Are they working correctly? That's one thing that Istio can do. We also give you the ability to observe traffic on those pods, the traffic between the pods, etc. What API calls are flowing between a service and two services or between individual pods. What's their performance of those calls? Are some of the pods offering a given service slower or faster than others to answer those API calls? All of that is available in Istio. So observability of your API level infrastructure. And security, the ability to say you can't make that connection, even though you want to make that API call, we're not going to allow that because you don't have the right privileges, or that API call must be encrypted in TLS in order for it to go through. That's another service that Istio offers. So what would you use traffic management for? Traffic management you might use for canary deployments or blue-green deployments. You might say I want 10% of my traffic to go to the new green version of this application, 90% to go to the blue, so I want to test the new green. I might do load balancing this way. Obviously, I do load balancing this way. I've got 20 blue pods offering the service. I need to spread load among them. I need to support multi-tenancy. I need to support retries. I don't necessarily want the application to have to do the retries. I want my underlying layer to do that. So you make a request into Istio or through Istio for an API, make an API request. That API request times out. Istio can resubmit that on your behalf rather than you building retry logic into your application. You might have circuit breakers. You know, this pod is pounding on this service so often that it's causing frankly, a denial of service attack. So you can set a circuit breaking rule and say pods can only make this many calls per second to this API, and you'll disconnect them if they don't. Timeouts, we sort of talked about retries, outlier detection. You have one blue pod that's much slower than all the others, so maybe you take that out of circulation. Because it's obviously not well. You can do rate limiting, sort of the same as circuit breaking. You can limit somebody as to how much traffic they send over a given API call. Tracing. You can trace your API calls, see where they're going, what pods they're talking to, etc. You can literally follow a layer 7 or layer 5 flow through the network. You can get all sorts of custom telemetry. You can meter, and some of the same things, and the same data that's used for outlier detection and rate limiting, et cetera, is made available to you through right now primarily Prometheus interface. So you can go look at how your infrastructure is performing at layer 5 through 7 layer, performance, et cetera. You can log some or all of the events in your network as well for analysis later. And Istio also provides security capabilities. You can have identity and authorization. I know what pod you are based on your labels. Are you authorized to make that API call you're trying to make? Based on your identity, I can encrypt your traffic using mutual TLS. all this can be driven by a policy. So that's, there's a lot of identity authorization and crypto capabilities within Istio. If we look at the components really quickly of Istio, the three main components are pilot, mixer, and auth, and then your proxy, and today the default proxy is Envoy. So pilot provides configuration data. So you write a policy that says things labeled X can send this API call to things labeled Y, or this type of API call to things labeled Y should be rate limited to 100 calls a second. That kind of configuration gets handled by pilot, and that gets pushed into the proxies on in all the pods. Authentication, the auth service takes your identity of those pods and creates certs and authentication rules, etc., as we talked about. Envoy is the actual data plane or whatever proxy you're using, but Envoy is the default right now, is the proxy that actually acts in the data plane. It's what catches the traffic from the given container in the pod and applies the Istio logic to it and sends it to the destination pod, which has another proxy, which can further act on the traffic before it gets delivered to the service. And Envoy is talking to Mixer to make decisions. So let's say you've got a rule that says this service can only make so much traffic, so many calls per second. Mixer can tell Envoy, well, how many times has that service made that call in the last second? So Envoy can make a decision if you're still in compliance or not. It's also where all the telemetry comes out and gets sent through. The last bit of this is Envoy. It's a very lightweight, fast, and modular HTTP gRPC proxy. It has control plane integration with Istio. It does service discovery. It can do health checks. It can do hot restarts, rolling updates. The nice thing about it, it fits very nicely with Kubernetes. This actually resides within each pod rather than in the host. So all of the application behaviors are wrapped within the pod, or all the service or microservices functions are wrapped within the pod, even though they're not in the same container. It's not a shared environment. So that means things like IP addresses are maintained, which Kubernetes, a number of things Kubernetes rely on. It means that your cryptographic circuits, certificates, which protect that endpoint, those are wrapped into the pod. So they're not shared globally. So, and it's also been hardened at scale. The entire Lyft infrastructure runs on Envoy. They're the original authors of Envoy, and it's a CNCF project. And we'll go through this. We've already talked about this. At this point, I'm going to go do this demo video. So before I do that, though, are there any questions before I go and do the demo video? No questions so far? Okay. So here's the demo video. I'll go ahead and I'm going to slow it down a little bit because it was a little bit fast. And let's go ahead and get this started. And again, as I said, this is what we did for OpenShift, but if you just replace any of the OC commands with kubectl commands, it has exactly the same effect. There's no OpenShift specific logic here. Just this is the video I could find on short notice. So we've got a number of pods running, and we're gonna look in all the namespaces. You'll see we've got the standard Kubernetes pods. We've got some Calico pods. And this is just your basic environment. So now you can pass the OC version. Yeah, that's now. If you take a look at the way we define hosts, again, this is probably not sufficient. This is just telling you how to stand up Calico in an OC in a OpenShift environment. That's not all that interesting here. So now we're going to watch pods as we create them. So we're going to start a demo, and there's a couple of policies in here which we'll talk about. So in this case, this is a policy. And what you, this is a replication controller for a service. I'm sorry. It's a replication controller for a service called the stars demo service. And there are back-end and front-end services and clients. The client's going to be the UI. And so we're going to now create those pods, the back-end and the front-end, and the user interface. And the user interface is that management UI. And now if you take a look at this, we have 3 pods talking together. We have a client, which is talking to a front end, and the front end is talking to a back end service. So this is standard 3-tier application model. What's showing here, the vertices are connections that are being allowed, and the nodes in the graph are the actual pods. So you can now see that the clients can talk to the front end and the back end, and the front end can talk to the back end, and the client can talk to the front end. Now, so it's a standard application. So you've deployed that, it's working. Now, you get told you need to deploy a PCI application as well. So we're going to create a PCI application that also needs to be connected to the client. And it's handling the PCI data in your application, in your service. So we have now we have a new back end and a new front end, and those are PCI compliant. And we've labeled them as PCI compliant. And that's this compliance. So they have 2 labels on them now, a role front end 2 and a role compliance PCI. So now let's do a kubectl create the PCI version. And you'll see we've added a couple more front ends and a couple more back ends. Now, we go ahead and add the PCI backend, the PCI containers in to the UI that we're using to tell the UI that it has some more nodes it needs to talk to. So that's just a little bit of housekeeping. And now the UI shows that everything can talk to everything. So this is great. Your application's running. PCI is the PCI application can be talked to by the container, by the client. So can the non-PCI. This is great. However, your security person comes by and says, what's this? Your front end, your client can talk directly to your back ends. That's not right. Your client should only be able to talk to the front ends. We talked about this. We said you can only have your client talk to the front end. So now we're going to tell Kubernetes, we're going to have Kubernetes install a policy that says default deny. And we're going to apply it, see this match labels to all pods. Basically, it'll match any pod because there's not a more specific saying match role front end or whatever. So it just says match everything. So we're now going to apply a policy that says no one can talk to anything, because that's the security guys having a connection. So when you do that, though, even the UI won't be able to talk to anything in the network, which means we wouldn't be able to visualize anything. So what we now have to do is add a policy that says we're going to allow the UI, the visualizer, to reach all of the pods. So that's what we just did there. And what it shows here is we're going to allow things from management UI role, we're going to allow, we're going to say we're allowed to talk to any service or any endpoint on the UI port. So now the management UI can see these pods. So these pods exist, but they're not talking to anything. Everything's down hard. Nothing's working in your application. Well, that didn't work. So now what we're going to do is we're going to create a front end. We're going to have a front end policy that basically says traffic ingress from the front end or from the client is allowed to talk to, on port 80, to things labeled, we're going to allow traffic in from the client from things labeled front end. So now the client, as you just saw that there, the client was able to talk to the two front ends. We do the same thing, except now we say the back ends are allowed to receive traffic from the front ends. So these are all the straight up YAML files. It doesn't matter if there's one back end or 1,000 back ends. This will all be dynamically applied. So now the client can talk to the front ends can talk to the back ends. But we still have now we've met the security team, standard front ends talk to back ends, client talk to front ends. The compliance guys see this, say, whoa, wait a second. Why can the non-PCI front end talk to the PCI back end or vice versa? We don't want that. Compliance says those have to be separate. So now we apply a policy that's going to allow us to filter traffic so that the front ends and the back ends will be limited. So only the PCI front end can talk to the PCI back end, and only the non-PCI front end can talk to the non-PCI back end. We're going to do that. I'm going to speed this up just a bit because we're a little short on time. The policies will look very similar to what you saw earlier. Same kind of policies. And now what you see is the front end, the normal front end can talk to the normal back end, the PCI front end can talk to the PCI back end, both front ends can talk to the client, none of the other connections are available. So now we've met compliance's requirements, the security team's requirements, and the application is working. And now it's independent of how many of these get stood up. You stand up a new version of the pod, so long as the labels stay the same, the policies will still apply. There's no firewall rules you had to update anywhere. There's no networking, which VPN or which VXLAN this gets installed in. You don't have to have any of those thoughts. It's just you deploy your workloads, you label them appropriately, you have simple policy statements that are human readable, that tell you what's allowed to talk to what, and you get the behavior you want in your infrastructure. And on that, I will end this slightly overlong presentation. I think we still have a couple of minutes for questions. I apologize for running a little bit long. So anyway, open for questions.
Yeah, first of all, thank you very much. I think we can have a few additional minutes to answer the questions. So are there any questions? You can send them to me via the chat, and then I will read them aloud.
So I see one here from Guru. What I showed, the demo I showed was just using Calico. We haven't integrated, integrating Istio into that would have been even longer, but we will be doing that. I think both technologies can exist on their own. Istio, you can just deploy Istio, or you can just deploy Calico. I think in the long run, both of them together are greater than the sum of the parts. So what we've very often seen is the first problem people have is just connecting their pods together, their containers together, and connecting them to the rest of the infrastructure so that things outside can talk to your pods and your services. So people deploy Calico to get the network running, simple, scalable, etc. And then they start using Calico policy And they might just be using standard kube proxy and other things for the service mesh. Then as the developers start wanting to get more feature-rich capabilities than what, say, kube proxy may be able to deliver, they then start looking at Istio. Or the security folks really want to control TLS encryption. You start looking at Istio. So they can go the other way, but usually what we've seen in practice is people start with Calico and then they're starting now to layer Istio on top of that to get that layer 5 through 7 functionality. We can make those slides available, yes. Guru, did that answer your question? As far as the question about the labels, we could have had those labeled as front end and back end and not front end 2 and back end 2. I think that was an artifact of the person who originally wrote the policy, and then we said, no, you should be using the compliant PCI label. We also wanted to make sure that the pods would show up differently labeled in the graph, but those could have all been labeled just front end and back end, and then had the PCI compliance label attached to it as well. And you have had the same effect, and just the graph would have looked been a little confusing. So that's why we had 2 different pod definitions there. Roy, regarding the network policies, are there Kubernetes, are they Kubernetes native, or do they rely on things in Calico? Most of the policies you saw there could be Kubernetes native. Calico has some additional capabilities. For example, Kubernetes, until very recently, did not support egress filters. That's a beta feature in 1.8. We've supported egress filters for a while. There are a few other things we can do in Calico policy that you can't do in Kubernetes, although that's slowly catching up. So I think everything you saw in that demo would work once you had egress policy filters in 1.8. So it's possible to do it with just straight up Kubernetes. You get some additional bells and whistles with Calico's superset. Please give a short comparison, Calico versus Contiv. Sure. I think the big issue is what I sort of outlined before. First of all, the policy is potentially, from a networking perspective, I haven't looked at Contiv's policy lately, but last time I looked, it wasn't quite as featureful as what we have in Calico. The bigger one is overlays, the reliance on overlays. And we think that's just a complication you don't necessarily need. Calico can run on an overlay network, but does not require overlays. I'm not adding extra technology to meet corner cases. So I think from a simplicity standpoint, there's just less moving parts in Calico compared to Contiv. Contributions, we're up in the dozens on Calico. Istio, I lost count, but there's quite a few people contributing to Istio. And from being used in production, we're aware of a very large, in orders of let's see how to put this correctly. Publicly announced, we see Calico as being the largest deployed implementation of Kubernetes network policy, and one of the 2 largest from a network connectivity, the other being Flannel, from a connectivity standpoint in Kubernetes. So it's very well taken up. Istio is not there yet, but Istio is growing very, very fast. So I don't have hard numbers on Istio. The k8s manifest used in the demo, like I said, there's a little bit of OpenShift-ishness in those manifests. None of the mechanics we were using were OpenShift, but there's some there. We will get a set of Kubernetes manifests out fairly soon. One thing we want to do is fix the stars demo. The stars demo is very fragile right now, so we're probably going to, and it's the stars backend is written in Ruby and is or Rust and is pretty fragile. So we'll probably do a bit of a rewrite there. So we'll make the manifest available, but there'll be a more solid version of this demo once we fix the visualization and Rust automation that underpins that demo. Calico versus Open Contrail. Again, I'd say the same thing. Our policy is much more Kubernetes-centric and less network-centric, much more pod and services-centric. We rely a lot on labels. We don't rely on networking artifacts like virtual networks and linking them with intermediate filters, firewalls, etc. We do this, all the filtering, all of the enforcement that happens right at the pod boundary, outside of the pod boundary, so it's trustworthy, but right there. And again, we're not relying on overlays. We're not building a lot of complexity overhead into this. So I think it's, again, the story is complexity, lack of simplicity and scale, and applying the policy in one place right at the edge of the network and doing it in a non-network specific manner. So anything else? I ran through a number of those questions. Anyone else have any questions? I can still hang around for a couple more minutes. Otherwise, up to you guys. Oh, back to you.
It seems as if all your questions, all the questions are answered. Yeah, thank you very much again for this nice session. Thank you all for joining. We will let you know as soon as the recording is available. And of course, if you have also interesting topics for our online meetup, just let us know, because of course we are always seeking for nice contributions. And yeah, I wish you all a very good day.
Actually, one more point, if that's okay. I'm sorry, whenever you're done, I've got one more point. If I'm allowed, a lot of this material we covered very quickly. What I forgot to mention, and it's the only plug for Tigera I'll do, is Tigera is now starting to offer training sessions around Istio and networking and policy, etc. So if anyone is interested in those, you can go to our website and look in the training heading, and we have classes, and those are offered remotely. So if anyone wants to learn more about this and how to actually use this in anger, obviously you can look at our documentation, etc., but also we're offering training classes. Sorry about that. That's all.
All right. So then we're done for today. I wish you all a good day. Thanks again for joining, and I hope to see you again next time. Yeah.
All right.
Goodbye to everyone.
Thank you.